This is the sky on the way in. It's a bit iffy at best, but we are going to make a go of it and try and observe. So this is going to be an observing evening, so talk followed by stargazing. And it might be a kind of cloud dodging type of stargazing, but we will do our best. So given that there's no tea and there's no second talk, it just leaves me to introduce Francesca De Angeli, who's going to talk about mapping our galaxy with Gaia. Francesca.
Despite the weather. My name is Francesca and I work here at the Institute. And tonight I'll talk to you about this European space mission called Gaia. More than 400 people around Europe have been collaborating to make this a success in preparation and in the operations and processing of the data. And I was lucky enough to be involved from the start of
Is your microphone on?
I think it is.
I think it's a speaker.
It is on. So maybe I'll try to hold it. Does that make? Yeah, it does. Okay, then I'll hold it. Okay. I assume what I said so far was not fundamental, so I'll go on. The goal of the mission, really, as the title hints, is to create a map of our galaxy, a census of more than 1 billion sources in our galaxy. Now, this is a very large number. It's difficult to grasp really how big it is, but if you count at 1 per second, it will take you 30 years to reach 1 billion. So that's how much, but it's only about 1% of our galaxy, so it's really just the tip of the iceberg still. So I talked about a map, but we should not think about a 2D map like we see, for instance, for most geographical maps nowadays. What we are building is actually a 3D map of our galaxy. And actually we are going even further because for many of the sources we have information on their velocity, not only in the plane that is perpendicular to our line of sight, but also in the direction of the line of sight, what we call radial velocities for a subset of the sources. So for a subset of the sources, we actually, which is anyway several million of sources, we have actually information in the 6-dimensional space, so positions, in 3D, but also velocities in all directions. So this is, of course, an amazing amount of information for astronomers around the world. And of course, on top of that, the catalog is enhanced by additional information on the brightness, colors, and other information, as I'll show you later on. What we are looking at here is what you have been looking for a few minutes, and I was glad to see that indeed, there was some silence because people were focusing on the animation that I'm showing. Is indeed an animation that is entirely based on the data produced by Gaia. So here, where the animation has several stages, let's say. So first, it shows you a patch of the sky that is centered in the Orion constellation, and then it zooms in. It gets closer to what is one of the closest clusters that we have, which is the Hyades, and now it's actually moving around, going around this cluster and showing, letting you appreciate what is the 3-dimensional structure of this cluster of just 100 of sources or thereabout. And finally, there is a stage where it shows you the motion of these sources. First with just arrows, and then indeed, well, of course, this is a fast-forward movie, but the stars, in fact, to the naked eye, they don't move at all. But how do we get from a 2D map to a 3-dimensional map? Well, we need to have information about the depth, the distance of these sources from us. And this is what is really challenging to measure in astronomy, because you are measuring distances to point-like sources that are extremely far away. And the way we do it is by looking at the apparent motion of these sources with respect to background sources when observed in different periods of the year. So this cartoon shows you the Earth going around the Sun, and you can, well, you can imagine that if you were to observe the same source at 6 months difference, you would see the source in a different position in the sky with respect to the surrounding sources, to sources that are further away. And this is because there is this apparent motion of the source due entirely to the fact that this source may be closer or more distant than others. So what we measure really is not the distance in itself, as we might imagine it, but is this apparent motion of the sources in the sky. This is measured as an angle, but of course the stars are so far away that these angles get to be really tiny, and you need absurd precisions in the instruments that we are using to measure this. So in the case of Gaia, for instance, well, the precision that we can reach is at the level of the microarcsecond, which is something that you can not even imagine, but just to give you an idea, we would be able to measure the size of a 2-pence coin on the moon at the distance of the moon. So this is how precise the measurement is. And of course, the situation is in fact much more complex than what can be seen in this cartoon, because not only the one star that moves, all of them will move of this apparent motion, which will be different depending on their distance from us, but also they will move because they have a true motion. So this is a more realistic case showing that everything moves in the sky at the precision at which we are measuring. And how can we actually disentangle what is the apparent motion and measure it, and measure as well at the same time what is the true motion of all these sources, of these 1 billion plus sources. So what we need to do is we need to take many measurements of each of these sources so that we can then reconstruct, modeling these two components, the true and apparent motion, for all of them, and measure these two quantities separately. And these will provide us information of distance on one side and true motion of the sources. This is achieved in Gaia by continuously scanning the sky. So Gaia, well, the nominal mission was designed to last 5 years. Now, in fact, an extension has already been granted for an additional year, and it's likely that we will get more. Sorry, it's just okay, so this is showing you, of course, an artistic impression of what the satellite looks like. The satellite continuously scanned the sky during these 5 years, and the expectation is that it will collect about 80 observations for each source in the sky. It's an average, of course. There will be some areas of the sky that will be observed more often. But basically, by spinning and by having its spin axis moving gradually during a 6 months period, the whole sky, it gets observed every 6 months, more or less. There are two fields of view. You can see here two beams, basically, because there are two areas of the sky being observed simultaneously, and the light from these two areas is focused onto the same focal plane. So you may wonder, but how, if the satellite is moving continuously, how do you get to have sharp images, which is what you need if you want to have very precise measurements of positions and motions? Why don't you get an image like this one, where you have trails for stars? Well, these are, of course, these images from Earth, and these trails are due to a long exposure and to the motion of the Earth. But Gaia moves, rotates even more rapidly than the Earth, so why don't we get trails? Well, this is where the design really gets clever. Gaia has has the largest camera that is in space at the moment. This is a view of the entire focal plane, which shows there are more than 100 CCDs. Each of these CCDs is a detector, similar to what we all have in our digital cameras and phones. and each CCD has about 9 million pixels. And you can think about these pixels as little buckets where the light, where the measurement is taken, because when the light hits the CCD, there is a light-sensitive coating on the surface of the CCD which will release electrons, and these electrons are then collected in these buckets. And what happens is that as the star moves along the CCD, the charges in the buckets are shuffled onto the next bucket in the line of sight in the along scan direction at the same speed at which the star is moving, so that the charges are actually accumulated, and you get a better observation by the end of the CCD. And there are of course many CCDs, so you can then put together all these observations and get even more precise measurements. This view also shows that there are different areas in the photoplane with different roles. So the largest part is where these white light images are taken, which are used for the measurements of the brightness and positions and proportions. But then there are other different types of CCD and with different optical paths that take dispersed images, so low and high resolution spectra of the sources that are crossing the focal plane. And this is where we get observation on the color and on the radial velocities and on chemical composition of the sources, so that we have really complete senses and information about these set of sources. The way the consortium working on this project works is that the data is processed as soon as possible, and then a catalog is prepared, and the catalog gets released straight away. There is no period where we can use the catalog for our own research before releasing it to the public. And already 2 releases have been done since the start of the mission. And this is a view graph summarizing what is the content of the current catalog. So you can see here, here you can see, first of all, big numbers, but also many different types of information that are contained in the catalog and available for these sources or for subsets of those. So you have positions, brightness, parallax, distances and proper motions. You have colors for many of the sources, but for a good fraction of the sources, you also have astrophysical parameters like the temperature, radius, luminosity of the sources. You have information about the extinction that the light of these sources is subject to, radial velocities, variability information, because many of these sources vary in brightness, and this depends on their physical properties, their evolutionary status, and a good 500,000 of these variable sources were classified for the catalog itself, and we even have orbital information for about 14,000 asteroids, and many more will be available in future releases, because there will be at least another 2 releases which will include more observations, so the data, the values that we provide will be even more precise, and we will have them available for more sources. Now, colors were one of the, from my point of view, they were a very important addition in the latest catalog that we released. This is again a map of the sky that is only showing star density, star counts really. Here the brightest areas are where we have measured more stars. Now there are some dark areas here as well, which very fine structure. These are not These are not areas where there are no stars. These are simply areas where there is some dust, interstellar medium, that prevents us from seeing the stars, particularly in the wavelength range where Gaia is taking its observations. Now with the latest release, we can have the same map in color, just using the colors measured by Gaia. this is a, well, really a beautiful map. You can zoom in as much as you want. You can see very fine structure even along the galactic plane. And it's really the first time you have a catalog with this precision that covers the entire sky and that is fully homogeneous in the processing and collection of data and everything. So it is really, this catalog has been released in April this year, and it is revolutionizing really the many branches of astronomy. Now I want to show you something else that uses the information on the brightness and colors and distances together to study the evolution of stars. So this, I don't know if you have ever seen a diagram similar to this, but this is what we call a Hertzsprung-Russell diagram, color magnitude diagram, and this is showing a sample of solar neighborhood sources with good quality brightness, colors, and distances in Gaia. It's only using Gaia data. And these, as you can see, stars locate position in this diagram in preferred locations, depending on their evolutionary status, their mass, their properties. So here you will have that bluer sources will be towards the left, bluer and hotter sources towards the left, whereas cooler and redder sources will be to your right. You can see that most of the sources distribute along these what we call main sequence. So it's the central sequence that goes from bottom right to top left. There is where that is where stars spend most of their life. You will have massive blue objects towards the top left and faint cooler and less massive objects towards the bottom right corner. When stars move off the main sequence, they usually follow what is called a giant branch, which is what you see here as a branch moving off the main sequence towards the top right corner. And there you will have, stars will increase their size when they get towards the end of their life, and depending on their mass, they will end up in different ways. A star of the size similar to our sun will not explode as a supernova like more massive stars, but will end up in yet another sequence, which is called the one of the white dwarfs. You can see it here, very well populated in the bottom left corner. So I don't know if you can appreciate this, but this diagram, well, first of all, you can see that all the different evolutionary stages are very well populated here, and the precision is such that, that you can distinguish very fine details. For instance, for the white dwarfs, it is the first time that we see quite clearly that there is a split between two different populations, depending on what kind of fuel they are still burning, how much hydrogen is left, if only helium is left to burn. This is something that had not been seen as clear as here with previous catalogs. So really the precision of the photometry as well, and of the distances, because here distances also matter, because the absolute luminosity has been adjusted for the distance of the sources. They are really of unprecedented quality. By knowing also the velocities of sources in this catalog, we can even trace back some of the history of our galaxy. We see today the Milky Way as a pretty quiet galaxy, not undergoing major collisions or disruptions. But from the velocity distribution of sources, it has become clear that the Milky Way did undergo a pretty major collision early on, about between 10 and 11 billion years ago, of course. At that time, the Milky Way was somewhat smaller, and it encountered a galaxy that was more or less the size of the Large Magellanic Cloud, so quite a sizable object. you can see the signature of this encounter in the distribution of the velocities that is shown in this plot. Here on the vertical axis, on the vertical axis you see the circular motion around the center of our galaxy. You can see that most of the sources concentrate at fairly low radial motion. So radial motion is in the horizontal axis, and you see they are pretty close to zero, but in radial motion, whereas in circular motion they have a value that is around 220 kilometers per second, which is what is the average motion here in the spiral, in the arm where we are. But here you can also see a different population, a clearly distinct population that has a circular motion that is nearly zero, but has large radial motions, up to 400 kilometers per second. This is clearly a signature of a population that has a different origin with respect to most of the stars. Different groups have actually studied this in detail and come up with the explanation of this collision earlier on of the Milky Way with another galaxy, and have given different names to this colliding galaxy. Now, the galaxy was really devoured by the Milky Way, and one of the funniest names that has been suggested is the sausage. So this is the Gaia sausage. Now, I think that, if you have to eat something, why not a sausage? But I don't think that's where the name came from. I think it's more because it relates to the distribution of these different population in the space of the velocities that we shown here. This is just, it's a simulation, it's a model, but a simulation that represents a similar encounter to the one that we think may have happened for the Milky Way earlier on. And you can see here how the colliding galaxy, the red stars, are fairly disrupted because of the collision with a bigger galaxy, the Milky Way. But they are still there, and they still preserve a memory of the different origin that they had, so a different distribution in the velocities, and also it has been shown also in their chemical composition. So this is a proven fact. And many more results have been obtained with this catalog, and many results are coming out on press on a daily basis. But here is where I leave you, and if there are questions, this is just a movie showing the preparation of the launch, so the unfolding of the solar shields, and then the preparation of the fairing and the rocket, which launched Gaia. The launch was in December 2013.
To what extent do you know, I guess, things like rate of change of velocity, orbital parameters, that kind of thing, as well as just the straight line velocity of objects? Is it mostly only very close by things, like in the solar system, where we have orbital parameters?
For the radial velocities, yes, at the moment the catalog is limited to sources brighter than 11 or 12 in magnitude, which means quite close indeed, or very bright sources further away. But eventually it will cover also a wider range. So at the moment we have 7 million sources with radial velocities, which is anyway more than any other radial velocity measurements achieved so far in any other survey. So summing them up. So it's really, and also the beauty of these catalog is that it covers the full sky. And it's unbiased after the selection. Yes.
How have you excluded other galaxies?
Well, we haven't actually, but the satellite, the software that runs on board and that detects the sources is designed to work well on point-like sources. So it will observe mostly resolved sources. So they can be sources from our galaxies. Indeed, we have a beautiful catalogue of the large and small Magellanic Clouds, which are other galaxies to the Milky Way. But what we will not observe are sources that are are galaxies that are so small that cannot be resolved into stars. In fact, we have observations of quasars, which are far away point-like sources, and the reference frame is based on those. Yeah.
So when the project finishes, what happens to the satellite?
Yeah, it will become one more piece of garbage up there. So at the moment, as I said, the mission was designed to last 5 years, which would mean that the mission completes in the summer of 2019, so fairly soon. We have already successfully applied for 1 year extension, but in fact there is fuel for another 4 years. So we could go on until 2024, so that at least we maximize the output of this. But yeah, at the end it will stay there. It's in L2, which is the second Lagrangian point, so it's quite far away. It's not a very busy point of the sky at the moment, but yeah, it's gradually becoming so. Yeah.
How did you choose the name?
Gaia. Well, I think initially, before my time, was an acronym because it was to be an interferometric instrument somehow. So the I stood for interferometry. Now it's not anymore, so the design changed since, so that is not the meaning anymore, and in fact it's usually not capitalized, not all letters are capitalized, it's not an acronym anymore. So now, yeah, it is the name of a goddess, but yeah, it's not for this reason that it was first chosen. Yes?
What's the little red bit that was at the black hole image?
The one that showed the galaxy collision?
Yeah.
That was the other galaxy. So it was a smaller galaxy, that one you mean, the one that you can see at the bottom there. It's a smaller galaxy that gradually gets closer and closer, and it gets devoured by the bigger galaxy. Of course, the gravitational force will attract this smaller galaxy toward the bigger one, and then once they get merged, the smaller one will lose its shape and get mixed up. Yes?
How long would that process take?
That's a good question, which I don't know the answer. I guess at least could be a billion years. But in fact, we can see that they are not fully mixed yet, and that we still have stars preserving memory of this even nowadays. And this is, they estimate this to have happened about 10 billion years ago. Yeah.
Is artifacts much of a problem?
Is
Artifacts, like from other,
yeah.
from the sun, for example.
Yes. Big problem.
How do you remove it?
Well, okay. There are the design was the satellite was designed to avoid, of course, the sun light to reach the focal plane with these big solar panels that you saw. They are there to make sure that the temperature of the payload is kept as constant as possible, and to keep the light of the sun far away. What happened instead is that after launch we realized that there were some fibers left at the edges of these solar panels that instead caused some of the light to get into the focal plane. This means basically an increase in the background level, which of course has consequences. But for the actually, we have seen that at the end of the day, of course, we had to adjust our calibrations to make them much more sensitive to sudden variation of the background light. But at the end, we succeeded recovering basically what could have been lost otherwise. And yes, sorry.
If it's constantly moving, then wouldn't you just get it all worked in round something or something? And
You mean the images all blurred with these stripes?
it just keeps going, like wherever it wants. And
Yeah, it keeps going.
everywhere.
What do you mean, the single stars? The images of the single
No,
stars?
like Gaia itself
Mhm.
would just move and wouldn't eventually it just go out of your galaxy because
Oh, no, because it's located in a special point, which is called Lagrangian point. So basically, it's a point where there is it's a dip in the potential created by the Sun and the Earth together as a system. But basically, what happens is that whatever is placed there doesn't move that much. It's a pretty stable place. So this is why the mission can actually last longer, because during the launch we didn't consume much fuel, and to keep it there we don't need much really fuel. There are sometimes occasions where we have station maneuvers and stuff like that where we use some, but otherwise in the normal operations the satellite stays where it should on its own.
So maybe time for one last question. And
Yes.
we'll
Given the data, do you run the simulation forward? And if so, how long have we got?
We run simulation forward, not as much forward as to see the galaxy exploding or but yes, we do. I mean, in fact, in the movie that I was showing, on the first slide, there was also some forward movement when the motions were shown. Yes. So of course that was a fast forward because otherwise you wouldn't see anything. But yes, of course what happens is that you create these fast forward movies, but you know that some of those star seeds will evolve by the time. So it's not just a question of the motion, but it's also a question of what happens to them. If they're very massive and they explode, then they might in fact affect also surrounding stars and or disappear altogether.
Cool. So yeah, I think we have to call it a day. So yeah, so first of all, let's thank Francesca. And yeah, secondly, the good news is that it's still clear. It's looking quite nice outside. So yes, go outside and do some stargazing. So for anyone that hasn't been before, there are maps outside. You can grab a map off the table and show you where to visit all the different telescopes.